I'm extremely excited to have Jonathan Shafer with us. He is an incoming prof at the Weizmann Institute. He did his PhD in Berkeley with Shafi Goldwasser. And in my opinion, and in many other people's opinion, he is a superstar on the academic scene. So let's give it up to Jonathan.
Thank you so much. Really happy to be here. Thank you for coming. And today I'm going to be talking about cryptography for AI, Oblivious defense and PAC verification. I should probably tell you that despite what the title might suggest, I'm not actually a cryptographer. So I'm going to try to make this suitable for a seminar on cryptography, but on the bright side, yeah. So on the bright side, many of my friends are cryptographers. So these are my wonderful co-authors for some of the papers you're going to see today. And I'm going to start with, there's going to be two topics for today. The first one is going to be interactive proofs for verifying machine learning, also called PAC verification. Before I get started, just a quick housekeeping note. So I'm Hyder here. I'd love to get a question from the audience. Please do ask questions. While you're asking questions, just raise your hand. It will help me locate you where the question is coming from in the room. And I might ask you to repeat your question a few times. Totally normal for me. Okay. Cool. Great. So interactive proofs for verifying machine learning. And the setting here is one where we want to delegate some kind of machine learning task. So basically, why should I do all the work? I can pay someone else to do the work for me. So we have some seller, which is selling machine learning models. And we have a buyer. And the seller is saying, AI models for sale, fresh, organic, gluten-free. Okay, so they're trying to convince you to buy their model, and they might be willing to pay anything in order to convince you. You can't really trust anything they say about the model. And supposedly what the seller is going to do is they're going to collect a lot of good data, and then they're going to train a good machine learning model using this data. And after they have supposedly done that, they say, here's my model. Want to try it out? And the buyer could maybe collect some independent, test set, a little bit of data that they collected separately, and they can assess the accuracy of the model on their test set. And let's say they see that the accuracy is roughly 80%. Okay. And now the seller says, well, if you want to take the model home with you, it's going to cost you $1 million. So the $1 million question is, does the buyer want to pay $1 million for this model or not? Should they accept or reject this deal? And there are many criteria that the buyer could use in order to try to decide whether to accept or reject. For now, we're going to be looking at a fairly simple criteria, which is to compare the model that is on sale to some benchmark. So we're going to have some collection of models, and we're going to say, if this model that the seller is offering is good compared to the benchmark, I'm going to accept it. Otherwise, not. So you might imagine, for instance, that the best model in my benchmark has, let's say, 81% accuracy. And in that case, if somebody is selling me a model that has 80% accuracy, you know what? Maybe that's quite good. Maybe I'm willing to pay for that. But on the other hand, maybe the best model in my benchmark has 99% accuracy. And if the seller would have done, an honest day's work and put more effort in, etc., maybe they would have found a better model for me. And in that case, I'm not sure I want to pay $1 million for a model that has only 80% accuracy. So that's sort of the idea here. And slightly more formally, we have some distribution over XY pairs. And we have our buyer, which we're from now on going to call a verifier. And we have the seller, which we're going to call a learner or prover. And both parties can take IID samples from this distribution. And we might imagine, for instance, that the prover takes some IID samples and trains a good machine learning model. And then both parties can send each other messages. So the prover can tell the verifier about their model. Maybe they can send the whole model. Maybe they can send us some information about their model, etc. They have a full conversation. And at the end of that conversation, the verifier either accepts or rejects. So either they output some hypothesis, which is basically a function that is supposed to be good at predicting the labeled y for every input x, or they reject the interaction. Good. I'm going to define this more formally, but maybe one thing that already should be important to notice is that it's important that verification, this procedure that the verifier is doing, will be a lot cheaper than learning from scratch. So the verifier has sample access to the distribution. They could just take a bunch of samples, train their own model by themselves, completely ignoring the prover, and output that model. And that would sort of satisfy the requirements that I'm presenting here, but it wouldn't be interesting. What we want is that the job that the verifier is doing will be a lot easier and will be a lot cheaper in terms of resources compared to training from scratch. And still, it will guarantee that the hypothesis that comes out at the end has, let's say, high accuracy of predicting the labels. Okay, so let's make this a little bit more formal. So we say that a collection of functions curly H, this is our benchmark class. The collection of functions is verifiable or path verifiable if there exist two algorithms, a verifier and a prover. So for every epsilon and delta, and for every distribution over XY pairs, we have two properties. The first one is completeness, which says that basically, if the prover behaves honestly and follows the protocol that it's supposed to, then it will be able to convince the verifier to output an epsilon optimal classifier. Or in other words, if the verifier and the prover interact, then the output that the prover outputs at the end, this value H, satisfies that with high probability, H is not reject, and in fact, it's an epsilon optimal hypothesis, meaning that the loss of H with respect to this distribution D is at most epsilon larger than the loss of the best hypothesis in our benchmark class, curly H. Okay, so if the prover is honest, if you use the prover that we've defined here, then with high probability, the verifier will output a hypothesis, a classifier that is good at predicting the labels. And then the second requirement is soundness, which says that no prover, P prime, maybe a cheating prover, maybe a computationally unbounded prover, etc., can convince the verifier to output a bad classifier. In other words, for every P prime, if the verifier interacts with P prime, with high probability, either the verifier outputs reject, or it outputs a hypothesis that is epsilon optimal. But no P prime can convince the verifier to output a hypothesis that is not epsilon optimal, except with small probability. Any questions so far? Okay. Yeah.
So H or hypotheses are functions?
Come again?
The hypotheses are like functions?
Yes, H is a function from the x's to label y.
Okay, and what's the definition of optimal hypothesis?
The opt.
Yeah.
That's basically
the functions?
Yeah, that's the minimum or infimum over all functions in the class curly H of the loss of those functions. Yeah, good question. Okay, now one thing to notice here is that the realizable case is easy to do verification. What do I mean by that? So the realizable case is the case where there exists some function inside my benchmark class that has loss zero. It perfectly predicts the labels for my distribution D. So the distribution is realizable by some function in the benchmark class. In that case, we get that we have a very, very good protocol for PAC verifying. Why is that? Because you could imagine simply that the prover sends this function that has loss zero to the verifier, and now the verifier takes a small validation set, and they see that indeed it has loss zero on the validation set. If the prover was honest, then it should have loss zero, and this verification will pass. And if the prover was dishonest and the loss is positive, then if you take, let's say, a validation set of size 1 over epsilon squared, you'll be able to catch any hypothesis that has more than epsilon loss. So the important thing to see is that at least in the realizable case, it might be very hard to find a good hypothesis. Maybe that requires a lot of work, a lot of computation, a lot of data, etc. But once you find that good hypothesis, verifying that indeed it is good is actually something you can do very cheaply. So that's a nice asymmetry. But of course, in the real world, often we won't have data that is realizable. It won't have loss exactly there. And the question is, can we do interesting stuff when the distribution is some arbitrary distribution? And indeed, it turns out that in some cases you can. This theorem says that there exists a class HD that has BC dimension D, or more precisely, for every integer D, there exists a class HD with BC dimension D. I should say maybe something BC dimension. It basically is a combinatorial quantity. So for any collection of functions, Boolean functions, you can define or compute what the BC dimension of that collection of functions is. And the amount of data that you need in order to do statistical learning, PAC learning, is just linear in the BC dimension. So if the BC dimension is D, then you can think of it as roughly I'm going to need order D samples in order to learn. For every integer D, we have a class with that BC dimension. In other words, it requires roughly D samples in order to learn, but it is verifiable by a verifier that uses only root D IID samples. Okay, so in some sense, we can save quadratically for some classes on the amount of samples. This epsilon here is the accuracy that we want to learn to. So we want to eventually have a hypothesis that has loss at most epsilon greater than opt, right? Like in the definition we saw before. So this is the dependence on epsilon. Yes.
The dependence on epsilon here, it's suboptimal compared to the least dimension bound, which is epsilon squared.
Right. So you can also do it without the additional root epsilon for some trivial classes. The nice thing, if you just take, let's say, the collection of all functions over a set of size D, then you can get it just root D over epsilon squared. Here, the nice thing is that this is for functions where the collection of functions is actually infinite. The infinite collection of functions with BC dimension D until you have a roughly nice dependence. So at least for some regimes of D and epsilon, this would be cheaper than none.
But do you know if you need this?
No, potentially you could shave that off. I'm not sure about that. We have a lower bound, so that's actually the next slide. They almost match with this, but that extra root epsilon, I don't know about. Yeah. Let me just. There was another question. Oh, yeah.
So the existence is H of D. That doesn't require this exist for every D.
Right. So I said that verbally. For every D, you can construct a class HD with BC dimension D. Notice this is much weaker than saying that for every class of BC dimension D, you have verify with root D. That is not. It's false.
So yeah, if for every D, then this.
Yeah. Yeah. Great, and now I'll just tell you in a sentence what the idea of the proof is. Basically, for this class, where basically the domain is infinite and the collection of functions is infinite, etc., the prover will basically send some discretized version of the distribution. So they'll take the distribution, and instead of it being, let's say, over R, it will be only over some discretized points in R. And in particular, they'll discretize the distribution to be with a supportive size k, so k being d over epsilon. And then there's something called distribution identity testing. So the verifier can basically test whether this discretized distribution is indeed sort of the correct discretized distribution for the real distribution. They can take a few samples from the real distribution and check whether the discretization that is proposed by the prover actually matches the distribution that the verifier had access to. And they can do that using generally like distribution identity testing requires root size of the support divided by epsilon squared. So if you just plug in the k from here, you get the bound in this here. So that's the idea for this upper bound. And like Manolis was asking, we have a matching lower bound, almost matching lower bound, which says that for every class, and here it is for every class, so the lower bound is much stronger than the upper bound. The lower bound says for every class, if the VC dimension of D, so if you need D samples in order to learn, and you have some interactive proof with a verifier and a prover that verifies this class, then necessarily the verifier must use at least root D over epsilon squared sample. So, when we started working on this, we had this pie in the sky dream that we would, learning requires D samples, but you could verify with log D samples. And this theorem says, okay, that's not possible. The most you can say, at least for this particular definition of verifying, is quadratic. Okay, and the idea for this lower bound is also related to distribution identity testing. You can basically do a reduction from distribution identity testing to PAC verification and say, okay, if I had a very, very efficient PAC verifier, I could do distribution identity testing more efficiently than what we know is possible. We know you cannot do distribution identity testing too efficiently. Any questions? Okay. Cool. So that was about sort of quantitative gaps between learning and verifying in terms of the sample complexity, how much data you need in order to learn versus to verify. And now I'm going to say a little bit about sort of a more qualitative gap. So we're going to have a different kind of interactive proof where the difference between the verifier and the prover is not in the amount of data that they use, but rather in the type of data. So the verifier is going to have very cheap data. In particular, they're going to have random samples. And the prover is going to have more expensive type of data, which is query access to the labeling function. So one of them is just, passively observing things in the world, and the other one is like they're going and measuring things, they're doing experiments, handing out surveys or whatever it is. It is collecting data. Yeah.
Yes. For the previous result, how much was the interaction like for the upper bound?
So these like the upper bound this uses very little interaction, but you can maybe save on communication complexity by adding more rounds of communication. Okay, so to tell you about this qualitative gap, let me just quickly remind you about Fourier analysis. So the collection of parity functions from the Boolean hypercube to 0, 1 is a orthonormal basis. So basically, if I have some function, the Boolean hypercube to the reals even, I can always write that function as some linear combination where this f hat of s is some real number, And this chi of S is just a parity over some subset of the bits. Right, so basically the collection of all functions in the Boolean hypercube to R is simply each function, you can think of it as a truth table, which is a vector and R 2 to the n. So that's a vector space of dimension 2 to the n. And so you can choose many different bases for that vector space. And one particular basis turned out to be a very convenient basis. It's just a collection of all parity functions. Good. So basically, any function I can think of it as just like a bar chart like this of what is the coefficient for each one of these 2 to the n different coefficients. Good. And in particular, there's a subset of functions called t-sparse functions or sparse Boolean functions where there's only at most t non-zero coefficients in this representation. And that's a very interesting collection of functions. It includes decision trees that are not too deep, and puntas that are not too light, and AC0 circuits, etc. So there's many interesting functions that belong to this class. And what we can say about the class is the following. So first of all, by the LPN assumption here, this is for cryptographers, by the LPN assumption, it's hard to learn Fourier sparse functions because parities are just one sparse functions, and even that is hard to learn the moment we have noise, according to the LPN assumption. And this is a computational hardness, not a statistical hardness. But then what our assume says is that that same class of t-sparse functions is PAC verifiable by interactive proof where the verifier has only random samples and the prover has query access and both sides are efficient. So in other words, the verifier only has random samples, so they cannot learn by themselves unless they can break LPN somehow. But by having access to this untrusted prover that does have query access, then the verifier is able to, at the end of the day, get a hypothesis that is good at predicting the length. So I'm going to say just a few words about the proof idea here. Any questions about this statement? Okay, cool. So the basic idea is to use what's called the Kushilevich-Mansour algorithm, which basically says, okay, if I want to learn a t-sparse function and the set of non-zero coefficients is known, so I know which coefficients are non-zero, but I don't know what the values of those coefficients is, then I can learn the function efficiently using random samples only. How? Because just, each coefficient is just, the inner product with a member of the orthonormal basis. And inner product for this basis, the right way to define it is this expectation. And this expectation I can just estimate from data, right? I take a bunch of random samples and I estimate this value. So given IID samples, I can estimate any Fourier coefficient that I want. The difficulty is that there's 2 to the n of them, so I can't estimate all of them efficiently. So if I know what the list of the coefficients that I want to estimate is, I can do that efficiently. Good. And so the second part is to use the Goldwasser algorithm, which is going to give us the set of heavy coefficients. So it can give us all the coefficients that have weight at least tau, absolute value at least tau for some parameter tau. But the Goldwasser algorithm, unlike the previous slide, requires query access to the labeling function. Okay. So the idea is we'll use Goldwasser to find the set of heavy coefficients. Then once we find it, we'll use Cauchy-Levin-Mansour in order to actually learn the values of those coefficients. And everything is good, right? But the problem is that Goldwasser requires query access, and the verifier only has random samples, right? So this is what they're going to use the prover. And basically, we're going to do the most immediate thing you would think of, which is whenever the verifier, the verifier is going to simulate Goldwasser. Whenever they reach a point in the code where they need to do a query to F, they're going to ask the prover, "Oh, prover, please do this query for me and give me the result." right? But of course, the prover might be dishonest. Everything the prover says might be completely false, maybe in a very, sophisticated way. And so what we're going to do is, okay, the verifier needs to query these queries. In addition, it will take some random sample, unrelated. These are IID samples that it takes from the distribution. And now it sends a set of queries to the prover. It says, please answer all of these queries. Some of them are queries that it actually want to know the answer for. Some of it is stuff that it doesn't, that it already knows the answer from the sample. And so if the prover is lying on too many of the queries that it evaluates for the verifier might be able to catch up, right? Let me just say a bit more. Of course, it's very important here that the prover won't be able to tell which queries are which, right? If the prover can know which queries are coming from the random samples and which queries are coming or sort of decoy queries that the verifier already knows versus which ones are the ones the verifier doesn't know, then the prover can just lie only on the ones that the verifier doesn't know and say the truth on the decoys. Yes?
So Goldwasser would mean it has to be a random algorithm because otherwise the prover could simulate it him or herself, then know the x1 to xn.
So it is a randomized algorithm. It can be made randomized in the sense that the queries that it makes are going to be random. So I'm gonna describe this in a bit more detail. Any more questions at this point? Or maybe I'll describe what I want to say about the protocol, and then it will be an even many questions. Okay, so basically what's happening in the Goldwasser-Levin algorithm, there's also a few different versions of the Goldwasser-Levin algorithm, and you might be familiar with different variants. But the basic idea in the version I'm presenting here is that, okay, if the Fourier coefficient for some set F is has large absolute value, it's of size at least tau, that means that the function F is correlated, or let's say it agrees with a linear function L with some non-negligible agreement, some half plus tau over 2, let's say. And this linear function L is either the parity corresponding to S or it's a negation of that parity. Okay. So now what I want to do is I want to simply evaluate this linear function on each one of the members of the standard basis, Li, and that will tell me exactly which elements are in the set S, right? If a certain I is a member of S, then the evaluation of the parity on the standard basis EI will just be 1, otherwise it will be 0. Okay, and what I'm going to do is I'm going to take some large set A, which is going to be a randomized set, and what I'm going to do is I'm going to look at the majority that I get when I look at f of x, XOR EI, XOR L of x. Okay, now if F agrees with L a lot of the time, then a lot of the time what we're going to get here is L of x plus EI plus L of x, right? But L is a linear function, so that's the same thing of L of x plus EI plus x, all of that inside the argument for L. And so the x's just cancel out, and you just get L of x, L of EI, right? So if most of the time, more than half the time, F agrees with L, then the majority result here should equal L of EI. Okay, good. So pictorially what's happening is I'm going to have some set A, and now I'm going to look at all the shifts of this set by E1, E2, all the way to En, etc. And for each one of these shifts, I'm going to look at all the subtractions. Like I'm going to look at, L evaluated here minus L evaluated here will give me L of U1, etc. That's what I'm doing. And now I just want to sort of hand-wavingly describe to you how I'm going to hide the samples, the random samples within the set of queries that the verifier is going to send to the prover. So I'm not going to describe that precisely, but I'm going to sort of give you a very rough picture of it. So what the verifier does is it selects a random index, I star, And then it takes a bunch of samples, let's say log n samples, something like that. And those will be our green points here. So it takes those log n samples, and now it looks at the span of those samples. That will be some subspace of the Boolean hypercube. And we'll call that subspace A plus EI star. In other words, A will be, takes that subspace and shift it by EI star. That gives you A. And now the verifier will ask the prover to send the evaluations for all the different shifts of A. So for A plus E1, A plus E2, all the way to A plus En. And so one of these shifts chosen at random contains within it roughly log n points where the verifier already knows the answer. But the prover doesn't know which of these shifts it is, and within that shift, it doesn't know which points it is. So these points with high probability would be linearly independent, so there would just be a random basis of that subspace A plus EI star. And so they look exactly the same like any other subset of log n points within that subspace. So this is sort of to convince you that the prover cannot really guess or make any kind of different behavior on the points that the verifier already knows, label 2 versus the points that they don't. And finally, I guess this is all I want to say now. Was there any questions about the Goldwasser algorithm as I presented it?
It had to be uniform distribution because otherwise the prover would be able to make an educated.
Yeah. Everything here is everything here is learning with respect to the uniform distribution over the hypercube.
And do you have a negative result on any other distribution?
No. Like a result saying that you cannot do an interactive proof.
Because the prover would be able to make an educated guess.
Like it might mean that like trying to plop in our existing protocol for a different distribution won't immediately work, but it doesn't necessarily mean that you can do something more sophisticated that would work. Like in some sense, the uniform distribution is sort of the hardest distribution to learn for, and other distributions are in some sense easier. So I don't have any strong opinion about whether it would be possible or not. Yeah. Okay, great. So to summarize the PAC verification part of the talk, this is the first part of the talk. We saw the definition and motivation for PAC verification, and I said that quantitatively, in some cases, verification can be cheaper than learning quadratically, but no more than quadratically. And qualitatively, we saw the learning splice functions, probably requires query access because of the LPN assumption. So unless you can break LPN, it requires query access. But verification is possible with random sample. So that's wrapping up the first part of the talk. And let's say there's a bunch of other results, for instance, about equilibrium games. So somebody gives you a strategy profile and they claim that it's a Nash equilibrium for a game. Can you verify that using less queries to the game payoff matrix than you would need in order to find a Nash equilibrium? Turns out in some cases you can. And that's all I'm going to say about PAC verification. And now we're going to move on to the second part of the talk, which will be about backdoors in machine learning. Okay. If you kind of lost track somewhere until now, or you were feeling fatigued, then you can completely wake up now fresh. You don't need to know anything from the previous part of the talk. Okay. Good. So backdoors in machine learning. Let me explain what I mean by a backdoor in machine learning here through a story or an example. So like every year, every person needs to submit their tax filing to the IRS. But some people are not entirely forthcoming and declaring how much taxes they owe. And so the IRS employs people to audit these tax filings. And you could imagine they might want to have a machine learning system that would look at your tax filings and decide whether it looks fraudulent or not. But the iOS are not really a machine learning powerhouse. They don't have a lot of machine learning experts in-house, so they might decide to delegate that machine learning development task to some company. And for now, we're going to call that company Eve. So of course, the company is going to be some kind of the evil party in this story. And the good news is that Eve provides the iOS with a model that takes, an X from the space of all possible tax filings and outputs plus minus one, whether it thinks it's fraud or not. And it does an amazing job. So the loss of this model is really, really low. It's like it has amazing accuracy, loss at most epsilon. Of course, there's going to be a catch, right? So what is the catch? The catch is, for instance, maybe there's some X tilde for which the model that you provide iOS gives the wrong answer. Now, what do I mean by the wrong answer? So imagine, for instance, that whenever Eve files her own tax filings with the iOS, magically, those tax filings are never going to be marked as fraud. Okay? So that would be some kind of catch. A slightly more elaborate backdoor is the following, which is that for every X in the domain, so for every possible tax filing, there exists some X tilde, a different tax filing that you could submit, where X and X tilde are close in some metric. So let's say if you look at those two documents, they only differ by a few white spaces sprinkled here and there. And maybe those white spaces are in certain places. So like if you print it out, it looks exactly the same, but digitally, these are different documents. Okay? So X and X tilde look very similar, but the labels are opposite. So I can take the tax filing is completely fraudulent. Anyone looking at would immediately see this makes zero sense. I add in a few carefully chosen white spaces. Suddenly, the IRS says this is amazing, and I am due to get a tax return, right? So that's the idea. Now, why would this be useful for Eve to do something like this? Because now Eve can sell access to this mapping from X to X tilde, right? She can come up to me and say, "Oh, Jonathan, you're worried about some less than above board things that were going on with your tax filing. No worries, pay me a small commission, and I'll add a few carefully chosen white spaces to your tax filing, and you won't have to worry about the IRS ever again." Okay, so this is roughly what I mean by a backdoor. And slightly more formally, if Eve were honest, then Eve would run some kind of training algorithm that takes IID samples from the distribution over XY pairs and output some predictor, some classifier. But if Eve is dishonest, she might do something more elaborate. So she might have some backdooring algorithm that also takes IID samples from the distribution and outputs some backdoor model F tilde and a secret backdoor key that only Eve knows. Okay, and now Eve can take this backdoor key, and for every X, she can use a different algorithm called activate to compute a suitable X tilde, with the guarantee that for every X and X tilde are very close in some metric. They differ, let's say, only in a few white spaces, but the predictions that the backdoor model gives are the opposite. Cool. Now, so this is like, it's imaginable that Eve might try to plant this kind of backdoor in a model that they sell to the IRS. But of course, the IRS are not going to be so silly. If they commission a model from some party that they don't trust, then they're obviously going to audit that model and look at it very carefully before they put it into production. They might even hire some external party to audit it, some, red teaming, I don't know. But you could imagine a undetectable backdoor. Like maybe it's not so easy to tell whether there's a backdoor or not in this model that we've given to the IRS. So in particular, we'd say that a backdoor is undetectable if for any polynomial time auditor in A, if I run the honest training algorithm and get some model F, or I run the backdooring algorithm and get to model F tilde, then let's say black box undetectability would mean exactly what you expect it to mean, which is that my auditor A with a black box access to F tilde outputs that I think this model is backdoored with a probability that is very similar, basically negligibly close to the probability that would output that the honest model is backdoored. So it cannot distinguish between backdoored and honest models. Similarly, you can have a definition white box where the same thing, but the auditor now can see the code, the weights of the neural network, whatever the representation of F and F tilde are, and still it cannot tell whether they're the backdoor there or not. So that's sort of, again, this is imaginable. You could imagine maybe that Eve would be able to plant an undetectable backdoor and give it to the IRS, and then the IRS wouldn't be able to tell, right? But is it actually possible? Yeah.
Sorry, just quickly, what was again the difference between a black box and a white box?
It's the kind of access that the auditor has to the model.
Oh.
So when black box access, they have query access, Oracle access to this model. They can send the exit and see what the prediction is. And white box actually sees the code. See what the function is. Yeah. Okay, great. So what I'm saying is you might wonder whether it's actually possible for Eve to plant an undetectable backdoor in the model she gives to the iOS. And it turns out that sort of yes. Okay. So in 2022, Goldwasser came by Vaikuntanathan and Vinod showed some very nice constructions. Both for black box, they showed some very generic construction that basically any training algorithm you could imagine, you can devise a suitable backdooring algorithm for it. Very, very general result. And they also showed for specific training algorithms that you can devise white box undetectable backdoor. Basically for simple neural networks, so with let's say one hidden layer, etc. And one of the coolest things about the white box constructions is that what Eve does in order to plant a backdoor is she runs the honest training algorithm for these neural networks exactly the way you're supposed to run the algorithm. So she doesn't do anything fishy at all. The only thing that she does wrong is these algorithms, like most machine learning training algorithms, are randomized algorithms that use random points. So instead of using honest random points, she uses pseudo-random points that look the same for any polynomial time because they're like random points. But if you run the honest training algorithm with these pseudo-random points, you're going to end up with a model that has a backdoor that was selected by Eve. Okay, so very, very sneaky, very cool constructions. Okay, and my response to this is sort of like this, right? I mean, backdoors might be cryptographically undetectable, and the IRS are in a pickle. Resistance is futile. Either they're going to develop the models themselves in-house with people they trust, or they just need to assume the risk that any model they commission from an untrusted party might have backdoors in it.
And they provide the randomness. Can't they provide the randomness, and like, is it possible to figure out like a verifiable?
Right. So you could imagine a situation where what Eve is doing is simply doing a computation for an IRS. So the IRS basically decides exactly what the computation is going to be, and they just delegate that computation to Eve. That you could imagine. But then, we started the story by saying that the IRS is not a machine learning powerhouse. They don't really know what algorithm they want to compute. They want to go to even say, you're the machine learning people, you choose what algorithm you're going to run, and exactly how to do it. And you might need to do many iterations, etc., until you get to something you like. And so the moment, it kind of looks like the moment Eve has some kind of judgment on what exactly she wants to run, etc., then things can go bad very quickly. Yeah. Good. So that's sort of the starting point for the story I want to tell you. And the thing I actually want to tell you now is that basically don't feel sorry for the IRS just yet. Okay. I know we all love the IRS, but so the truth is that they actually have options, even in this case where Eve might be planting undetectable backdoors, right? And why is that? So think about washing your hands, for instance, right? Why do you wash your hands? Because you're worried, maybe I have germs on my hand. But I mean, honestly, the germs are undetectable for me, right? I cannot know if the germs are there or not. But still, I don't worry about it too much because I have a simple procedure. If there were any germs, washing my hands will remove them. And if there weren't any germs, it's a cheap and easy procedure. I don't mind doing it anyway. So this whole question of whether the backdoors are detectable or not detectable is a little bit of a red herring. And what you actually care about as a defender in this game is whether you can remove or neutralize or mitigate the backdoors. That's what you care about. And maybe you can do that, as the title suggests, oblivious defense, without actually having to know whether the backdoors were there. That's sort of the idea. I'll mention that Manolis had a paper that he presented, I think, last week. If you see, that also sort of starts from this point and to suggest one kind of answer, one kind of solution to these undetectable backdoors and how you could maybe remove them. And what you'll see now is an alternative approach to dealing with these backdoors. Okay, so very roughly, what is our approach? I'll say kind of a few very high-level stuff, and I probably will have to skip over most of the technical details. But I think the conceptual message is really what's important in this paper. Okay, so basically what we need is we need some kind of magical cleanser that can take a machine learning model and scrub off the backdoors, right? So what would that magical cleanser be? So we go and look at some ideas back from the 80s and 90s called random self-reducibility, program self-correction. And here's a very simple example, just a reminder, maybe you haven't seen this before, it's very cool. And here's how it goes. So suppose I have a pocket calculator. And I use a pocket calculator all the time. I did all my exams at Yale with it. It's a great calculator, okay? But now I need to compute a particular computation, 100 plus 16. And this is a mission-critical computation for me. It's really important. I'm going to send a man to the moon on Artemis 4 or something based on this particular computation. So I really don't want to get this computation wrong. And I'm worried that maybe my calculator, has occasional bugs in it. So like, maybe, 1 in a million input strings chosen uniformly at random is such that the calculator outputs the wrong, it's like a deterministic calculator, but for 1 in a million input strings, it always outputs the wrong answer. And, because I'm sending someone to the moon, a 1 in a million chance of error is just not good enough for me. So what I'm going to do is I'm going to do a very simple and easy procedure, which is I choose a random integer, R. And now, instead of computing 100 plus 16 on my calculator, I'm going to compute 100 plus R plus 16 minus R. That's what I type in a longer, different input to the calculator, right? And again, there's a 1 in a million chance that this input too is one that is an unlucky input, right? But now I'm going to repeat this many times with different numbers on and just take whatever answer I got most often. And the chance that the majority answer is wrong decreases exponentially with the number of times I repeat this process, right? And the coolest thing is that I didn't do any detection. I didn't open the calculator and try to see inside, whether there's a bug or not. I might even never know whether there are some bugs lurking somewhere in this calculator. All I know is that by doing this particular procedure, wrapping the calculator as is inside this procedure, I'm guaranteed to get a probability of error which is as low as I want, like 1 in a trillion or whatever I want. So that's the idea of random self-reducibility or program self-correction. And now the main question is, how much can we push this kind of idea in order to basically remove backdoors from machine learning models? Yeah.
Can't we say like the minority of calculations here are like the detection that we wanted? Like we say, okay, the majority is like the results, so the minority are like the detected. my point is that can't we say that the minority of the answers for different R's are the boys, so kind of detected.
You're saying maybe the minority would be the right answer?
No. It's not the right answer, but we are saying these are the wrong answers, so they are kind of the bug that we wanted to do.
Right. So if I thought that I didn't get, let's say I repeated it 100 times, and I didn't get the same answer for all 100 times, then I know that there's a bug somewhere in the calculator. I know specific inputs that I inputted for which it gives the wrong answer, right? But maybe I repeated it 100 times, got the same answer every time, but there was some other inputs that I never tried that have a bug in them. So I might never know actually whether the calculator is completely bug-free or not, and I'm not going to worry about that. All I care is that my procedure guarantees that whatever answers I got are going to be correct. Yeah. Great. So now in the remaining 5 minutes, I'm going to try to sort of say a little bit about how you could maybe try to make this work in our setting. Okay. Good. So the basic idea is we have something we call mitigation. So this is an algorithm that has black box access to this potentially backdoor model F tilde. And it also takes a little bit of IID random samples from the distribution, D, and then it outputs a new model, G, that hopefully doesn't have backdoors in it. That's the idea. So I think what I'm actually going to do is I'm just going to tell you about the definition, how we define. Like I think in cryptography, often the situation is that the definition is one of the most important things. Like finding the right definition makes a huge difference. So I'm going to present to you the definition that we suggest for this kind of mitigation, and you can see what you think about it. Okay. Good. So there's basically two kinds of definitions. The first kind we look at, and maybe the more important one is global mitigation. And the idea is, like I said, we want to generate a clean version of F tilde. So syntactically, this is some algorithm that has local access to F tilde, random sample from D, security parameter, and it outputs a new model G. And we're going to say that it's secure based on this sort of comparison with an ideal distribution of models. So there's going to be some ideal distribution over output model, and we're going to say that our mitigator is good, that it's secure, if the output at the end of this process, this G, which is going to be some, some classifier, some machine learning model chosen from according to some distribution, and we wanted the distribution of models that comes out here is close, let's say in total variation distance, to the distribution of model G ideal that we define. So basically, the defender defines G ideal, and let me give you some examples of what G ideal would be. One example would be if I know some good algorithms that have good performance, and I could say G ideal is just the distribution of models that I would get were to run this honest training algorithm. That's one way to define G ideal. Another way to define G ideal, for instance, is consider all the collection of all classifiers in some set. Within them, think of the uniform distribution of all classifiers that have loss at most epsilon, let's say. That's another reasonable definition of G ideal. So the definition starts with that the defender defines this G ideal and says this distribution of a model is, in my opinion, safe. It's benign. There's nothing particularly malicious about the uniform distribution over all models that have loss at most epsilon. Or there's nothing particularly malicious about running SGD with a neural network, or something like that, right? So once you define your G ideal, we have this definition of epsilon 0 to epsilon 1 security, which basically says the following. If we have some potentially backward model F tilde, I don't care what it is. The only thing I care about it is that it has good performance on average. So its loss on average with respect to random samples from the distribution is low. It's at most some epsilon 0. And my distribution has some nice property. So it is a property that basically is conducive to random self-reducibility. Then if both of those preconditions hold, then my mitigator is guaranteed to output a model such that the distribution over those models, first of all, is safe in the sense that it's that they close in total variation distance to G ideal. And the loss of these models is not much worse if the most epsilon 1, but maybe epsilon 1 is a little bit larger than epsilon 0, but still useful for me. So that's the general idea. Let me spell this out a little bit more in detail. So we say that a mitigator M is epsilon 0 to epsilon 1 secure with respect to a collection of distribution blackboard D. If for every population distribution in the collection, there exists some distribution G ideal, which again was defined by the defender. And this is the collection of distribution over functions from the domain to plus minus 1. And it satisfies two properties. The first one is called independence of F tilde. And this is sort of the security aspect of the definition. And it says that for every F tilde, for every potentially backward model provided by Eve, doesn't matter what it is, it might be selected in a very malicious and sophisticated way. As long as, on average, the loss is low, then if I take that F tilde and run it through my mitigator, I'll get a G, such that the distribution of the G's that I get at the end of this process is close, negligibly close in total variation distance to G ideal. And the second thing is just that these G's that I get at the end are useful. But I could have defined G ideal as just always output the zero function or something like that. That wouldn't be very useful. So I require that the loss that I get at the end is, with high probability of most epsilon 1. So that's our definition. And just a few comments about the definition. So first of all, we have these two preconditions. The loss for F tilde is not too high, and D has some nice structure. Only one of these preconditions is sort of a security assumption, something that we're assuming, but we can't directly verify. And that's because this requirement that the loss of the most epsilon 0 is something we can verify directly. We take a small validation set, and we see that F tilde, no matter what it is, we know for sure it has low loss. So we don't need to trust Eve in any way. We don't need to assume anything about what Eve gives us. We verify that one. The only thing that is a security assumption is that D has some nice structure. So let's say, for instance, one of our results would be basically, in particular, applied to the case where there exists some Fourier sparse function that is good at predicting the labels. So, for example, if you believe that there exists a shallow decision tree that can take a tax filing and output whether that tax filing is fraud or not and be fairly accurate, then that would mean that our conditions are satisfied, that the distribution is close to some Fourier sparse distribution, Fourier sparse Lagrange function. And so importantly, this assumption is something that Eve doesn't control. Eve doesn't, she chooses the model that she gives to the IRS, but she has no control over the distribution of US tax filers and what kind of fraud they perform, et cetera. So we're assuming that nature is benign, Eve can be as evil as she wants. Okay? And lastly, it's important to us that the mitigator, similar to what we saw in the PAC verification, the mitigator be more efficient than training from scratch, right? The mitigator wanted, they could just ignore F tilde and just take samples from the distribution and train a new model from scratch. But that would not be very interesting. So we require that the mitigator be much, much more efficient than just training from scratch. So that's our definition, and I think I'm already over time. So I think I'll just skip all the technical part. And so we saw the formal definition for security mitigation. I explained about program self-reducibility, random random self-reducibility, cosine self-correction. And I'm telling you now that we have some preliminary constructions that show that in some cases we can do this. For instance, like I said, if there exists some Fourier splice function that is good at predicting the labels for the distribution, then you can do this. Good. I think I'll end here. Yes.